All right. Good morning, everyone. Welcome to the second day of PLDI. My name is Ilya Sergey, and this is the session on program synthesis. It is my great pleasure to start the program with the talk for a paper that got one of the distinguished paper awards. So please pay attention. This work is on trace-guided inductive synthesis of functional programs, and the talk is given by Yongwei. On to you, please.
Thank you. Hi, everyone. I'm Yongwei Yuan from Purdue University. Today, I'm going to talk about trace-guided inductive synthesis of recursive functional programs. This is a joint work with Arjun, Radhakrishna, and Roopsha, Samanta. Let's begin with what's the synthesis problem? What are the inputs to our synthesizer? First, there are type definitions. For example, a natural number is either 0 or the successor of another natural number. And we will use literals like 0, 1, 2 in the talk. There are also type signature of the program we want to synthesize. Here, we want to synthesize net add that takes two natural numbers, x and y, and returns their addition. Along with the type signature, we're also given input-output examples that specify the behavior of the program. For instance, when applied to 2 and 1, the program net add should return 3. We may also take background functions, but this is omitted in the talk for simplicity. So what's special about synthesizing recursive programs? Generally speaking, there are two styles of inductive synthesis, top-down and bottom-up. In top-down synthesis, we start with an empty hole and gradually fill the hole with partial programs. For example, if we want to return a program that returns 3, it is sufficient to find a program that returns 2 and return its successor. But if we want to make a recursive call, it's not clear what value the input arguments here should be. In bottom synthesis, we enumerate programs in the order of increasing size and get rid of programs that evaluate to the same value to speed up the enumeration. However, we cannot directly evaluate a recursive call like net at x0. To sum up, the problem is that we only have partial information about recursive calls. There has been a lot of cool work attempting to address the recursion challenge. Here, we highlight a few. Early on, Smith and Asher either requires or ask user to provide input-output examples that cover the entire recursion trace. More recently, Smith and Burst seek to alleviate such user burden by leveraging novel semantics to enable inductive reasoning. The progress made by Smith and Burst is wonderful, but the problem is still not solved. What can go wrong? Here are 3 programs that are all consistent with the given example. Which program does the user intend? In other words, how do we resolve the ambiguity between these programs? Prior work typically resolve ambiguity by choosing the smallest program, which is, in this case, succinct. But obviously, succinct does not compute the addition of 2 input numbers. In fact, only one of them generalizes to all possible inputs. The problem is that a program being consistent with the given input-output examples does not necessarily mean it will generalize to all possible inputs. We propose a recursion trace-guided synthesis approach that tackles the challenges of generalization and ambiguity resolution in inductive synthesis of recursive functional programs without burdening the user. Under the hood, we developed a new version space algebra for representation and manipulation of consistent program recursion trace pairs. Note that the version space returned by our algorithm contains all satisfying programs along with their corresponding recursion trace under certain constraint. At last, we package them along with other goodies into a synthesizer called Syrup. Now, let's discuss what are traces or recursion traces and how they can help us. A recursion trace is a sequence of input-output examples that witness the evaluation of recursive programs. For instance, when we apply sucx to x equals 2 or y equals 1, it directly returns 3 without making any recursive calls. So its recursion trace is just a single input output example. When we apply the second program to input x equals 2, y equals 1, it makes a recursive call on 2 and 0 and directly returns its output 3. Similarly, when we apply the third program to the same input x equals 2, y equals 1, it first makes a recursive call to 1 and 1, and then in turn make a recursive call on 0 and 1. At last, it returns the successor of 1, which is 3. Note that all instances of recursion traces here are linear for simplicity, but recursion traces are actually trees. In the paper, we formalize this concept and define so-called trace witness semantics to relate programs and traces. Well, why do we care about recursion trace? Recall that all these programs are consistent with our given example. That is, they return 3 when applied to 2 and 1. How do we tell which one is more likely to generalize to all inputs? The most common strategy here is to choose the smallest program. But as we discussed, sucx does not generalize to all inputs. Even if we just focus on the 2 recursive programs, they happen to have the same number of AST nodes. But we know only the last one generalizes to all inputs. It seems that everyone's favorite inductive bias, program size, does not work well here. Inspired by prior work, we turn to an inductive bias that goes beyond program syntax and incorporates program semantics. Here, we choose recursion trace to be the semantics because it nicely captures the behavior of recursive programs. The question is, how do we incorporate recursion trace into program synthesis? Say we start with the given example, and we find a set of programs that returns 3 when applied to 2 and 1, but only if the program returns 2 when applied to 1 and 1. We regard the new example, net at 1, 1 equals 2, as the assumption about the program being synthesized. And we repeat the same procedure for the new example until there's no need to make further assumptions. This procedure described here follows what's called angelic semantics. And here we use it to search programs and traces in a cooperative fashion. As a result, each program set corresponds to either a recursive step or a base case. By taking the intersection of these program sets, we have a set of programs consistent with not only the given example, but also the recursion truth to the left. In order to enable effective program selection, we cannot just be satisfied with one consistent program trace pair. Instead, we want to find as many such pairs as possible. Similar to the previous slide, but this time we want to build a recursion trace graph rather than a single recursion trace. We regard the given example as the root node of the graph. We infer assumptions about the program and add them as children nodes. And we repeat the procedure for the children nodes until we reach base case for all the recursion traces. Now, we have a directed acyclic graph where each rooted path denotes a recursion trace. And the intersection of program sets along a trace contains program consistent with that trace. Note that if we consider recursion traces that are trees, then the graph will become what's called end-of graph. Please refer to our paper for more details about them and also trace-guided synthesis. In order to make trace-guided synthesis scalable, we adopt version space algebra, allow us to compactly store a set of programs consistent with a specific specification. For instance, the version space on the right happens to only contain those programs that are consistent with our given example. For lack of time, we do not discuss how to build a version space from scratch. In the paper, we also extend standard version space algebra with a new operator called pi to handle conditional expressions. To sum up what we achieved by using trace-guided synthesis, we have a complete set of programs consistent with the given example. The programs are also indexed by their corresponding recursion traces. Here are the 3 consistent program trace pairs we've been discussing in the talk. A non-recursive program, succinct, a program that recurs on the second argument, and a program that returns on the first argument. Now, we can use recursion trace as semantic bias to resolve the ambiguity between these programs. To evaluate our technique, we use 43 synthesis tasks from prior work and compare our tool Syrup with state-of-the-art synthesizer in the domain, Smith and Burst. And we mainly want to answer 2 questions. First, how does Syrup perform in terms of generalizability? To measure generalizability, we spawn synthesis instances using different input-output example set. And we calculate the percentage of instances where a synthesizer is able to return a program that generalize. The second question is, how sensitive is Syrup's performance to the quality of examples? In order to simulate users with different levels of expertise, we use different strategies to generate input examples. We obtain expert examples by sampling examples from recursion traces. We obtain random example by generating random inputs and evaluate reference implementation. And we also consider their variance by including or excluding the base case example. Let's first focus on expert examples. Here, we illustrate the percentage of examples needed from a recursion trace to achieve different target success rates. As we can see, regardless of the target success rate, Syrup always needs less examples to achieve it. So we can conclude that Syrup has better generalizability, at least on expert example. Now we move on to more diverse example sets. Here, we fix the number of examples used in each synthesis instance to be 3, and compare synthesizer success rate. Recall the 4 example classes we talked. There are random without base case, random with base case, expert without base case, and expert with base case. We observed that, in general, synthesizers perform better when given expert examples compared to random example, or when the base case is included. But surprisingly, Syrup's performance is only affected to a minimal extent by the quality of the examples. In conclusion, we propose a trace-guided synthesis approach that cooperatively search programs and traces. The synthesis is powered by a new version space algebra, and we use recursion trace as semantic bias to select program returned to the user. As a result, we are able to find programs that generalize better without requiring much effort from the user. Thank you. And now I'm happy to answer any questions.
All right, we have 5 minutes for questions. Thank you, Yongwei. Here is the microphone. If you have a question, please approach and state your name and affiliation. And we also have a Discord channel, which is quite easy to identify, so you might ask your questions there in the corresponding thread. There are no questions there so far.
All right. Hello. I'm Dave Holland from Galois. Have you thought about how you might use a formal specification, if you have a formal specification for your synthesis, to generate these traces? Because it's clearly, the traces clearly give you leverage that an ordinary specification doesn't have.
Sorry, can you speak a little bit? Speak up a little bit.
Okay. So I was wondering if you had thought about how you might generate these
traces?
Traces, yeah, from a formal specification that is not a trace.
Yes, that's also plausible, but it's certainly an interesting way to compare the 2 methods, given. But I guess here we use recursion trace as a way to summarize the semantics of program to address the inductive bias. But I guess if you have complete specification, then maybe the argument is more weak. But it's certainly an interesting way to see how that performs.
No. If you have a complete specification, it doesn't give you the recursive information still. So the traces actually have, these recursion traces actually have more information. And so I was wondering if you could figure out a way to generate those or synthesize those. Let's talk afterwards.
Okay, yeah, let's talk offline.
Hey, great talk. Nadia from UC San Diego. So I have two questions, actually. So first of all, I'm very excited about this semantic bias notion that you're talking about. And you said that it's based on the traces, but I still kind of didn't catch what the ordering is on the traces that you use to form the bias. And is it like learned? Is it, manually
Right,
defined?
good question. So here, in this work, because the task we look at is relatively simple, and like we just prefer, in general, like you can think of it's longer traces. The heuristic is quite simple, but I think it's certainly worth exploring, like more maybe learn the bias or learn to rank the traces in some way.
Oh, so longer traces are better.
Oh, in the paper we just like use a simple heuristic, like return the longest traces for one with the longest.
And what's the intuition behind longer traces being better?
Yes. So we noticed that like it's easy for like synthesizer to return just a trivial non-recursive program, and when you come to like this functional program that doing data structure transformation, it makes more sense to say a program that takes more advantage of the input, recurs more on the input data structure. So I guess that's the kind of the heuristic behind.
Got it. Thanks. And my second question was about, so you showed that it has better generalizability than these other techniques, but is there a trade-off in terms of synthesis times?
Yes.
Okay.
So synthesis time is it's comparable, but we do see there's admittedly there's scalability problem, especially when given random example, because the short answer is like when give random examples, there's a larger search space we need to explore, because we are exploring all the trace for one pairs. When given random example, there's more trace need to be explored. So there's some trade-off there. But yeah, on this benchmark, the time is comparable.
Awesome, thanks.
Thank you.
More questions?
Hi, nice work, Aditya from UIUC. If I understand it correctly, you're making equivalent programs that have the same trace and using that as your version space algebra. Is my understanding correct there?
You're asking if
you're generating traces, you're making them up, and then collapsing programs that have the same trace instead of random, different-looking things that waste your time by having the same trace.
So I guess that's more like a high-level intuition. Like under the hood, we have some more complex operation defined. How to. So we're not just, in short, like we're not just collapsing programs along a trace. Like we need to, because we need to track all the recursion traces, and that's not scalable.
Right. That's where my question was. So how do you choose what traces to make up? I mean, you said you branch on these options, and then you have this DAG.
Right.
I can give you 2,0 could go to 2,45, and I can still think of a program that can do that.
Right.
It'd be stupid, but
So we are not kind of doing backtracking. Like you remember the graph we were showing? Like we're not kind of backtracking on that graph, but rather we're kind of constructing a version space that that kind of corresponds to the entire graph, and then we choose program from that graph.
But your graph does represent every program that can give you any possible trace of, let's say, a bounded length on the examples given to you?
Yes, things like that. We have like a syntactic constraint on the program size, and we construct a version space that contains all the satisfying programs within that constraint.
Okay.
All right. In the interest of time, let's take the rest of the questions offline, and thank Yongwei again for a very nice talk.